Good afternoon, ladies and gentlemen. We'll go ahead and get started. I have 3:15. This is, of course, Windows Vista Heat Management Enhancements. Adrian Meninescu is here with us and asking lots of questions. He's smart, so thank you.
Hi, thank you for listening. Hi, everyone. My name is Adrian Meninescu. I am development lead in kernel group. I joined Microsoft about 8 years ago. Working on two kernel components, object management, local procedure call, and also user mode component, actually half user, half kernel, the heap management. So I came here with the white notebook, and people thought I'm going to have the presentation on a Mac. Well, in fact, it's not how it looks outside, it's how it looks inside. This is an x86 running Vista. I'm going to, in some details about the Vista heap management and how we did about improvement in this area. So let's get started. I assume everyone here has at least some basics about the heap management, what the functions are, to malloc, free, and that kind of stuff. What is the role of the heap management? And I have just one question, actually. So who tried before to write heap exploits? Only one? Oh, two. Okay. So maybe I don't see very well. And who was successfully running heap exploits after SP2? Well, it doesn't really make statistical sense because there are a few people, but anyway. It became harder after that, and we try to make it even harder from now on. So I'm going to talk a little bit about the basis of the heap management. I'll cover the main structures that were involved before in exploits and are interesting from the security researchers. And I'll give some brief about evolution of the heap management. Then I'm going to dive into the Windows Vista heap, where I'll cover the security enhancement, I'll cover the performance and reliability enhancement, and also the new role of the Vista heap management, where we want to look at the Vista heap as a tool to improve the quality of other applications, including third party. At the end, we hope we have some time for some questions and answers, and also we have a bunch of demos showing some structures or some of the internal things in the heap management to see how it looks today. So security is an industry-wide concern. I don't have to argue about this. Anyone in this room understands this, and I'll just skip through this. I'm just making the point that it was a very important shift in Microsoft culture through trustworthy computing, where we are thinking from the security, we're thinking of security from a completely different, different perspective. And the heap management development is just one example of that, but you saw in previous talks, in many other components, we had a completely different approach. You have a much better thinking about how the security has to be thought to the process from end to end. And the anti-heap management has the improvements in Vista to address two things. So one is a strategic point in defense, and from the second perspective, it has to address the industry trend with respect to memory usage and multi-core scenarios, and introducing more 64-bit relevance to 64-bit computings. So back to the basics. The first significant change in the heap management was during the NT4 Service Pack 4, when the heap look-asides were introduced to address performance issues. Later on, during XP and Server 2003, and later on in 2003, some performance problems were addressed with the low fragmentation heap, which is a new front-end heap management introduced back then. And I'm going to discuss a little bit what is the architecture for the low fragmentation heap. And at the same time, in the security community, the heap exploits became more visible. And at that time in XP, Service Pack 2, and Windows Server 2003, we had the first round of heap mitigations where we tried to take away the low-hanging fruits that people will use to run arbitrary code on a machine. And now in Windows Vista heap, we had an even bigger step forward. First to address the next exploits, the next round of exploits that were found, and also to increase the performance and address performance problems such as fragmentation, scalability on multiprocessor machines, and such. So here is the, a broad overview where the heap code lies on, and you can see at the top is very thin layer of the heap wrapper functions that are exposed to applications in kernel 32 DLL. And here you can find functions such as heap alloc, heap free, heap realloc, so all these heap star functions, as well as global alloc, global free, local alloc, local free, and so on. That stuff is really boring from a security perspective. It's just a scene, right? So I'm going to dive in the anti-DLL part where the biggest part of the anti-heap management is implemented on. And I would like to focus on, there are three things you might need to consider here. We have a management of a big chunk of memory we get from the system, and this is the segment management. We may have an optional front-end heap, which examples that would be the low fragmentation heap or the leukocyte heap. And every single block that is over 500K, where the virtual threshold is, on 32-bit machines, are just direct call to virtual alloc. And the heap manager just keeps track of its allocations in order to release the memory when the heap is destroyed. So these are like the basic structures I'm going to refer in these talks, so I'll mention here. And I just wanted to focus on two things here. There is an array of 128 list entries. Let me see the mouse works. Yeah, so 127 of them are dedicated to hold free blocks of a particular size. You have like free list for 8 blocks, 8 bytes blocks, list for 16 bytes blocks, and so on, up to 1K. And there is one special list entry there for every single block that is over 1K. Every number I mentioned before only applies for the 32-bit platform. On 64-bit, all these numbers are doubled, so it depends on the granularity. And the non-dedicated free list started to be indexed. It has some hash to have a quick constant time lookup later, but it's not really interesting for this presentation. Another thing, the second thing I want you to notice here, there is an array of segments which manage the memory allocated from the system. And the array is limited to 64 entries. And the size of the segment usually grows in time in an exponential manner. So as we reach a limit and we try to expand the heap, the next segment is going to be to have the same size as the previous, as the entire heap usage before. So it's going to double every time, up to the moment where we reach a limit and we have to allocate as much as we can from the operating system. So inside the heap segment, there could be areas committed and uncommitted. So most of the time, the last segment in the array has a large uncommitted range, which is used like in time to allocate to commit more memory. Most of other segments will have uncommitted spaces all over the places, and even the last segment can also have uncommitted spaces over the places. So if we look at the committed space, here are the allocations that we give to the applications, and every single allocation every single block has a header in the front that is used by the heap management to handle the request and to track the allocations, to track the free space, and so on. And those structures are actually very interesting for exploits because using that may trigger some code paths to be executed, and eventually end up in running some arbitrary code that that is intended by the exploit. So let's take a look a bit at the heap entry structure. So we have a size of the block, we have a preview size of the block in some granularity, and this is used by the heap manager to locate the adjacent blocks. So based on the size, we know where the next block is. Based on the previous size, we know where the previous block is. We also have some flags controlling some whether the block is free or busy, whether this is virtual block, or whether this is right before an uncommitted range, so we prevent touching the pages that were not committed. You can see below, like from a debugger, how we used to be the heap entry in debugger a long time ago. Right after that, there's another structure present in the free blocks, and that was really very interesting for exploits. You probably are already familiar with those methods to use the free list removal. So the operation when we try to remove an entry from the free list to have an arbitrary write at the address with a value controlled by an exploit. And here is how the code used to look like a long time ago before the first heap mitigations. So we have here fetching the forward link pointer, and the next instruction we fetch the backward link pointer, and the next one is actually writing at the backward link pointer value we fetch from the list the value from the forward link pointer. So you can see this as a translation from an exploit perspective as how you can basically deter the heap algorithms to have an arbitrary write. And there are several variations to this. So one would be, have a buffer overrun. You go over the Rex header and you put there a free list entry even if the block wasn't free before. And there are some other variations involving virtual lock blocks, and you have the list entry in the front of the entry. So regardless, there are like several ways the exploits took advantage of that. Another component of the heap manager is the look-aside list, and you can think about those as some sort of caches that the heap manager keeps on the front of the heap manager to have a very fast operation to alloc and free. All the blocks in the look-asides are not coalesced with the free blocks, and everything is disabled from that respect. The algorithms take no locks. Everything is done with the non-blocking low-level primitives. And the header looks pretty much as a busy block. And interesting here is it just have just one pointer for the next block in this list. And the problem with the look-aside blocks, with the look-aside heaps, was that when we move toward like multi-processor scenarios and highly scalable servers, we may have contention, we may have cache collisions on the list entries. So like multiple threads running on multiple processor at the same time may try to do a push or pop operation for that S list, and that is going to invalidate the cache line for the processor. So this effect can be seen very easy in some of the benchmarks, and I'm going to show later what the problem is. And the low fragmentation heap addressed that problem to begin with. It had a different mechanism to handle concurrency and to handle multiprocessor scenarios, and at the same time changes the allocation model so that will behave much better on large on large processes, on large heaps. And essentially, it's very tough to have a very short explanation of how this low fragmentation heap really works. You can think at some individual allocator, bucket size allocator, and every single bucket has its own management for the concurrency, has its own management for the memory allocator and the policies and so on. And also the granularity of the allocation, the internal fragmentation increases with the block size, and with 128 entries we handle 16K allocations. every single block in the low fragmentation heap has also an entry that is in the front of the allocation. And, but the structure is different than the regular heap block. And you can see there a pointer to a subsegment, which is the structure which manages the allocations and manages the blocks in this subsegment. And the heap manager needs to locate that entry in order to do a free operations to push this block to a list. And it also has the flags and also keeps track of the unused bytes. And the unused bytes are useful because in some scenarios you really need to know exactly the size that the application requested and not to round up to the size we gave away. So there are some mitigations that were added in Server 2003 and in Windows XP Service Pack 2. And this was basically to take away the low-hanging fruit that were found that were very well published out there to be used in exploit. As I mentioned before, it was a very reliable method using the list entry removal operation to have an arbitrary write. So we added this check before we remove, before we do any single write to the block entry. We added this check, which is, so we have this entry here, we have a pointer to the next block, the forward pointer is going to the next block, and this block needs to have a back pointer, has to go back to the same entry. So we have this round loop that we have to reach the same entry back. And the same for the backward pointer. We go back to the previous block, and following the forward pointer, we have to reach the same entry. So if these conditions are not met, we do not write anything in the memory, so we deter this arbitrary write that used to be very, very, very common before. We also at the same time an 8-bit cookie that is tested on free, but also interesting and very, very significant seems to be the encoding of the low fragmentation heap entry. And this is that subsegment that we use to locate the entry that for free. Is actually a randomized pointer now based on some random number, based on the address of the block, and also based on the heap address. And the function itself doesn't even matter, there's just some sort of those parameters. The thing is, it doesn't allow you to copy from one place to another this random block. So assuming you get from some way some information on what the random value is, so what the cookie value is, it has to be applied for the next block. So it's dependent on the context of the block. And as far as I know, and let me know if I'm wrong here, there is no way around this mitigation unless like you have a brute force attack or you attack the actual data inside the block. And this seems to be still the case today. Now, after these mitigations, there are some changes in the landscape. And from security perspective, there are like new methods of exploits surfaced. Some of them were involved LucasCi, some of them were involved the list array of free blocks. And on the same time, we also look from the performance perspective where we have seen an increase in memory usage for applications. So applications really explode. You can see very commonly, it's a very common scenario to buy a computer with the 1 gigabyte of memory now. The memory is much cheaper, it's more affordable. And the same application, the software, take advantage of that as well. On the same time, the way the hardware manufacturers actually increase the speed of the computer seems to stop with adding like more gigahertz to the processor. It's more to add like more cores and more CPUs on the machines, and this becomes more and more available. So we have to make sure that the anti-heap management is faster by default. And the hardware can take advantage of and the software can take advantage of the hardware advances. And at the same time, we have an increased role in 64-bit computing. And the 64-bit computing comes with new scenarios and new problems. We have to address larger heaps, like over 2 gigs that we used to before. And this was the condition, the changes in landscape that trigger some of the heap changes you see here. And at the same time, it is this question, what we do for the application developers, what we do for like even internal developers, to make sure that we don't allow, we're not tolerate too many of the, so many like code bugs, so many heap errors. How can we make the heap find the problems much earlier when in development phase? And this is the code quality, which is another role that we took on the heap management development as well. But before we start and do a lot of changes in the heap management, we have to look at this pie. And this is like our constraints we have when we go about some changes here. So we have from one side the performance, and this is very critical for high-end servers. This is very critical also for client applications. And on the other side, we have the security, where it's not about the vulnerability in the heap management, it's about the vulnerability that some other components or some other applications running on Windows may expose, and how can we mitigate the effect of those vulnerabilities. And also very important is the compatibility. So from security perspective, correct, the security meaning was like, let's say 10 years ago, just correctness. So we have to respect the contract. We have to make sure the API works exactly as advertised. If someone asks like for 8 bytes, we can give less than 8 bytes to cause the buffer overruns then. So it's about correctness. And security actually didn't even make the pie, wouldn't make that pie like 10 years ago because it was a must be there. You can't have like functionality, even if it's faster, it doesn't matter. If it's not correct, it's not there. However, it was a shift in the culture, as I mentioned before. And we look at the heap management, okay, so it not only has to be correct, the heap itself, but also what can be done to increase the role as a line of defense for heap exploits. And there are two roles here that I would like you to see. So one is we attempt to mitigate the effect of an attack. So instead of like allowing someone to elevate the privilege and run arbitrary code or something like that, we'd rather crash the process or terminate the process right away. And on the other side, we'd like to see the attempts of attacks where we'd like to make difficult for people to hide, like brute force attacks, kind of the brute force attacks. Sorry. Now, if you look at the performance side, we have to remember that the heap management has to scale from very small devices to large end servers. And this is a very challenging task because it's a wide variety of patterns that the heap manager is exercised to, and it also has to follow the industry trend. So the applications like 15 years ago are completely different from the heap management perspective as are today, and actually it's not only from that perspective. And you see a huge increase in memory usage, you see increase in relevance of symmetric multi-computing, and also the hardware advances as well. And here is the interesting thing as well, which is the compatibility. And the compatibility is not about the heap management changing the interfaces. Let's say I just add a new parameter to a function, so this is not going to work. No, this is about the internal functionality that some application took advantage of sometimes by mistake, by ignorance, and sometimes just because they try to be smart on something. So I could give you an example. For instance, we have an issue at some point with a process was ported for 64-bit, for 32-bit to 64-bit platform. And was noticed that was using a large amount of memory, much more than it used to be on 32-bit. And we can see on sometimes on 64-bit platforms, the structure may be bigger, the pointer is big, so, it used to be like a few megabytes memory usage. but you can see some gigabytes, so even if you compare the pointers, you can't really see how this can happen. And when looking to this problem was something very interesting happening there, because that process has some sort of handling, some throttling method, where it handled like low memory resources, but also some other resources that try to detect were increased. And instead, so you have like two options to handle this. You can make a function call to optimize or reduce the resource consumption, or you can be smart about this, which is you can make a function call to heap management, allocate a ridiculous amount of memory, and that for sure is going to fail. And then the exception, and that is going to raise an exception if the heap was set for that, and catching the exception is going to handle the memory condition. And what happened actually on 64-bit, that succeeded. And instead of throttling resources, you get even more memory usage. And this was like, just one scenario I can tell, but people can rely sometimes in realloc returning the same pointer back. Sometimes they rely to write or read from the block after they call a free. And some changes in the heap policy, such as returning the last block released first, may actually cause some troubles to that applications. And also, see whether a process has some compatibility problem, it's sometimes a challenge as well, because sometimes it depends on some conditions. It could be just, some crashes right away and that's easy to spot. Sometimes you can see some missing functionality that is hidden somewhere, like buried somewhere inside the menu and so on. And sometimes you can see some performance regression. So having those constraints, you have to think like we have to look at every single change we do and every single innovation we do here, looking from all these directions to understand what the compatibility impact is and what the performance impact can be and how we can help us with security as well. And one simple example was let's say someone said, we can actually add, place to prevent buffer overruns. We can place every allocation at the end of the page and have a guard page somewhere after that. So that will catch like buffer overruns right on. Well, we have already that for years. We have the page heap, we have the application verifier, and we do that a lot. But for a tiled build, this is really a problem for the performance, and this is why. Just imagine you have a process, a server application, which barely fits in 2 gigabytes of memory. Now, let's say you have 8 bytes allocations, that kind of fills all this 2 gigabytes memory. So from 8 bytes, you have to take one page for the allocation itself and another page for the guard page. So from 8 bytes, you get to 8K memory. Now, in a 2 gig space, you kind of need 2 terabytes, 2 terabytes address space to have that application running as it used to be. And also the commit space, which kind of, which involves like, which may involve frequent paging or like would request like a large amount of memory is going to be a challenge as well. So some of those things kind of may look from a security perspective very, very appealing and very good to do, but from practical perspective may have some troubles. So, but here's how we proceed with Vista. And I'm going to start with the security features first. And we have first some block metadata randomization. We have integrity check on every single entry. We have randomization on the base address, and we also have randomization on the function pointer that some people probably noticed exists in the heap structure already. And we have algorithm variations in response to usage pattern. And I'm going to go through this a bit as well. We have also more frequent, we have actually more frequent termination on errors. And the feature was to be before as well, but I'm going to discuss how it's implemented differently in Vista. So block metadata randomization. So this is a very simple, XOR algorithm. The goal for that is to make it very difficult for an exploit to guess the right value to be put in place to hide an attack attempt, or to prevent a crash, or to prevent, or to execute something that is controlled by the exploit. And obviously needs to have a very low performance impact, as I mentioned before. And we also took the stand to restructure the heap management code to have a very flexible and very contained algorithm, so it can be very easily updated. So as we find out about some way around those things, we can very easily go about those and change the structure, change the algorithm, and so on. So we want to be agile in updates. And another point here is the integrity check, which is part of the header, part of the block entry is hashed to a 8-bit value. And the previous 8-bit cookie that was added as a heap mitigation a long time ago has been repurposed for that thing. In fact, some other fields were repurposed as well. I'm going to show from debugger how this looks these days. And the value itself that we find for the checksum is randomized along to the header. So that happens before the entire header is randomized. And the value itself is actually validated every time we need to touch that block internally. So if we need, let's say, to free a block, we need to coalesce with the next block, we had to basically decode the block entry, and at that time we verify the checksum. So it's going to make much difficult to, for exploits to hard, and also we may find errors much earlier on than we used to do in the retail in the retail heap. Okay, so it's time for a demo now. Okay, so let's just take a program here. I'll just pick. Oops. So here you can see the list of the heaps as the process starts up. This is the initial breakpoint, so it didn't really run to the entire initialization code yet. So several other heaps are created after this point. So as you see, the default behavior, if you set it under debugger, is to have all the debug options on. And this behavior was like that since for a very long time, so we keep the same way. But this is not really interesting for this demo. I just wanted to show you like the debug functionality on this one. If we really want to get the retail heap under debugger, we can specify this HED option in the debugger, so we get the actual retail bit. So you can see there is no debug options now in the heap manager. And here is a different way of looking at dumping the heap blocks. And we can see that some of them have already the low fragmentation heap enabled. Some of them are not. So let's just pick the VCRT heap, which is this one here. And here you have a full dump of the heap allocations. So let's just take one block from this heap, and I don't know, just take this one. And let's dump the header. So you can see the size of this block, it's 3D to 0. And here is how the header looks like these days. So if you remember the slide when I showed how it used to be before, you used to see here the size, here used to see the previous size, and so on. Now, it's more like, it's kind of difficult actually to understand what's happening, like, because part of this header is really encoded, like this part here and this part here over here. And this is going to be very difficult to debug, but we have debug extension to actually look inside the entry. And here you can see parallel, how this block entry looks from the debugger after it has been decoded. So now you can see, for instance, like the size of the block, you can see also the flags, and here is the checksum. And this is the same detailed right here. So you can see the checksum over there, which is A2, which currently is just some simple algorithm between like a XOR between these three bytes, but it's not really relevant, can be changed, as I said before, in a very flexible way. Also, the segment management changed by itself, and is going to be discussed a bit later. So the segment index that used to be available in the heap entry before, now it's actually an offset to the 64K boundary to the actual end of the beginning of the segment. And also interesting from the debugger perspective is that you have the validation of the checksum all the time, and you also have validation of the free list. So if we take like a free block over here, you also have the validation here of the free list entry, which means that this is the forward B pointer. So you can see the forward and backward is going to go back to the same address of here, which is like 8 bytes offset to this one. And the same is going to happen for the backward pointer and forward. So this is like, so this is like how this heap entry looks like these days. And the fields have been shuffled a little bit around. So you have the previous size now in this position compared to like this position that used to be before. And some of the flags has been repurposed for other things I'm going to show a bit later. So we have an internal knowledge of the internal heap allocations and so on. So the heap manager, for performance improvements, actually has a lot of changes in the algorithm. Has a lot of changes in algorithms to adapt to pattern usage, to adapt to detect like a particular fragmentation scenario, to detect particular contention on a heap usage. So at runtime, switches some of the policy and some of the algorithms to use either LFH, and even inside LFH, there are some other policies, finger policies as well. And these changes in the runtime may have some security implications in the sense that you have to understand what is the current state of the heap before you start building an attack. And it's also shifting the way the heap behaves in a brute force attacks as well. And this may also involve including commit and decommit policies, which are interesting because it may actually cause some access violations as well if the memory happened to get uncommitted as well. And going further to even more heap randomizations, this is something that has been asked a long time ago. The heap-based address is now randomized within certain limits, and there are some restrictions to this, the same as for ASLR. And this is, you can't really place a heap in the middle of the address space because you can block an application to allocate a large amount of memory, like 1 gig and so on. You have scenarios like that. On the other side, there may be some performance impact because of TLB misses, for instance, and or some other faults that can happen in the memory manager. So we have to take into account all these constraints if you look from the heap perspective, and we came with some numbers of random value we can choose from, and we're still fine-tuning this value itself. And the same, it used to be a function pointer inside the heap manager that was exploits some exploit that he knew about them, and that by itself was randomized with a cookie as well. And going back to and to show those structures here, I'll just go to the same structure. So okay, so you have these heap addresses these days, right? Let's just try it again. Right. So you see, it's a completely different heap addresses, right? So this versus this one. I think I skipped it. Yeah. And well, there's an exception here with the address that is in a share section for a heap that's placed in a shared section. And inside the heap manager, you can see, for instance, you can see, for instance, that the function pointer that used to be like plain null pointer does some exploits to get advantage and replaces something else. It's now is now a completely different value, and the same you can see like the coding key that is used for the heap entries. So this is per heap random value, and also you may notice that. Somewhere at the end, somewhere in this area used to be a large array of free list entries, which is no longer available in Vista Heap Management. We combined the functionality of the non-dedicated list with for the small free list entries, and now this is not available anymore. And there also used to be some other structure like the Lucas site, which is also no longer the case here. So. Another thing I wanted to show is like some of the heaps in this process have the LFH enabled, some of them have not. So when you start the process right on, probably none of them have LFH enabled, probably. But as we detect some of the pattern usage, we enable this the low fragmentation in some cases. So you can see, for instance, in this heap. So you can see, for instance, in this heap, when you dump the statistics of the heap usages, that those blocks, like in the range 16 to 24 bytes and so on, low fragmentation heap is used. But for other blocks, the allocations go to the anti-heap manager, and this is very likely to happen for the most common sizes, or if we have contention on the heap lock. Okay, so now the question that was even a long time ago was, okay, so we detect some inconsistency in data. Let's say you find that the forward, backward, and so on, the list entry is invalid, is incorrect. And okay, so what to do about that? And this is a very tough answer because, if I take the security hat, I can say, well, we should terminate the process. This is like an attack. We should just terminate the process. There is no way we have to live with that. On the other side, if you look at the compatibility perspective, some applications have nothing to do with the network, has no exposure to any attacks whatsoever. And actually, if you look for the broader area of applications that run on Vista, the percentage that was really of the interest is on the focus on the security researchers. It's a very, very small percentage of that. So for all of those things, we have to kind of see what do you have to draw the line? What do you have to know when we can actually, take the security very seriously and have no tolerance for these errors, and where we can leave this application running because it's harmless, not networking facing, and so on. And back then, in Windows 2003 and XP SP2, we had a global flag which can be like system-wide as a policy. It also can be like per process or per image base. And when that flag was on, we issued a DBG breakpoint, and that may end up in Dr. Watson, or if people handle that, maybe nothing happened. And however, in Vista, we come up with a way, so we enable applications or processes that have security at a very high standard to choose security versus compatibility. So they have a way now, actually several ways now, to make this choice. And if any inconsistency in the data or any corruption we detect at runtime, then we're going to make this call to Windows error reporting and terminate the process. And there is no exception passing and anything like that people can handle to to catch this up front. And the scope is process wide. you cannot say this heap can crash, this cannot crash. Once you set it, the entire process, no matter what the heap is, no matter what the cause is going to terminate as soon as you detect an inconsistency. Detailed information is also available in dump files. And currently we have no plan to provide the functions to disable it, and we want to stick with that, but there might be some things with respect to compatibility, and we have to find a way to enable those. Yeah? No, so currently there is no way to turn on randomization. Currently there is no way to turn on. Yeah? Sorry? So I think you have a choice to actually replace the default debugger, which is the default behavior as the program crashes, right? And that thing, it's actually, so if you replace this and if you launch the debugger, you can have control from, because you get the exception before happens. Let's say you have a access violation in the heap manager. You are going to see an exception first because we see a debugger attached to this. And you can actually intercept from that point on. So it has to act as a debugger for that. So if you don't run into a crash, then what is the problem? Yeah. So okay, so if we detect something, if we have debugger attached, we first allow the debugger to take control over that place, right? So you can define your tool wherever as a debugger and take advantage of that functionality. Make sense now? So, okay, so we took the stand that 64-bit platforms have this termination on by default. And this is very easy because there is no much compatibility in 64 land at all. And the same, we did a lot for the 32-bit applications that were built for Vista. The components that ship with Windows Vista, most of them have this functionality enabled. And here is a programmatic way, like some component or some applications can enable this functionality. And this has been already documented in MSDN and is available in the Vista build. This is using the heap set information. It's a new information class added to this call. If your component is critical for security, actually, I recommend anyone would use this thing at all. I recommend anyone will use this function because even if it's not important for security, it's also important for reliability and for code quality. And sometimes, you have to pay support costs and so on to understand where the problem is. And information about corruption is going to be available in debugger, as I'm going to show right now. So I have a demo here with the process which has a few memory problems. So okay, this is the code, and it has the font size so that makes it easier. So basically, I'm going to go through like 3 scenarios. So one is freeing a random pointer from the stack to the heap manager. Another one would be doing a malloc and having a buffer overrun with this pointer, with this value over the pointer, and then subsequent heap operation after that. And I also have some leaks if we have time to go to this as well. So let's see. Okay, so let's see what happens if we start this process. Actually, okay, so you see this error code here, critical error detected, and This is when the heap manager detected that an invalid heap operation happened. This is the free of a stack pointer to the heap manager. And we can see that the application has this enabled by default. And this will be going to be the hard way because there is some glitch in the debugger extension right now. So this is the value that we check before we break inside the debugger. So that was supposed to be some random value there. 0 is clearly not a good one. If it's 0 or anything but that value, the heap is going to break. So even if you, so the idea would be to make difficult for someone to guess the right value to disable the entire functionality. So let's go to this again. And let's do it a bit different. So we saw this, so let's say it's running. And you see after this DBG breakpoint that happened in the debugger, we saw actually the actual Windows error reporting showing up the dialog and the process is terminated. So this stack, variable of the free stack in this particular case is not really harmless. So even if that happened, we can detect earlier and prevent some corruption to happen to the heap. But we really want to be very rigorous on the heap management functions. So a process which wouldn't have this application enabled will do something like, let me try this again. Okay, so this is not really interesting. Now this is interesting. So this is in the heap management code when we try to see what is our current policy to break in debugger. So we read this value over there, and let's unassemble a little bit before. So it was this comparison that was failing back there, right? And if we look at the value of EAX, this was the random cookie we expected to see in this particular case, in this process on this instance. If you run this several times, you see something else. And let's go back again, and let's put the right value over there. Actually. So this one here. Okay, so now it shows out the right value. And let's try to move the instruction pointer back one instruction. So we get this comparison again. Okay, so let's execute this code again. And now you see we have the same test, but now we take the branch, and we actually skip all the breaking in debugger that for this process. And this is what happens for processes which have the enable break on corruptions off. So if we continue to run, this is the normal exit of the process, and as you see, there is nothing. There is no no trace, no anything that something really bad happened to this process at all. Okay. So let's just pick like another process here. Yes, I have some time for this. So let's just pick now like an SVC host somewhere here. So this is, the count is limited, so I can't really open this process. So I have to enable to run as admin. Actually, so let's pick this again, yeah. Okay, so now we are successful. So if we look at this, oops. So this was like an arbitrary services process running inside Windows. So this has the termination on corruption also enabled. And as I said before, we took the stand to have most of the Windows components in the loop for this one. And okay, so going back to the slides, I'd like to make the awareness that the heap manager also can be seen as a tool in increasing the code quality. So all these early detection methods, everything that was done before, actually helps people to find bugs much earlier in the production process, and fixing vulnerabilities and defects in the product. The cost for that actually changes from the independent stages of the product. So if you detect that very early on, before even checking the code, then it's more effective. You know, the developer can just, fix the bug, find the problem, fix the bug, and that's it. If the code is checked in, a large number of people are going to be affected by this, depending on the size of the group, depending on the, how many developers and testers and so on are going to be impacted by the same change. And if it's very difficult to find, those bugs, those defects can actually stay there for quite a long time. And once the product is shipped, the cost of fixing that thing is it's even more higher. So we want to set the trend in the industry for the Windows development that we have less tolerance to low, to poor quality of the code. We want to make sure the heap functions are properly used, the buffer are properly sized, and we want to make sure that we detect and we cache this as soon as possible. And we encourage anyone to enable the termination on error as appropriate. And furthermore, we expect that in time is going to reduce the compatibility impact we have today. Because as people develop more applications, starting with Windows Vista and so on, we expect to have less applications exposing heap overruns and double free and other errors that used before, because they can see this in production in development phase. So now, if we look back, what we did in Windows Vista and what were the known attack vectors after Server 2003 and XP SP2. First, we removed the Lucas side list and the array of list entries that were the next low-hanging fruit that I heard of. Today, I'm not aware of any real exploit that was built on top on that. They were more like a proof of concepts, if I understood very well. But there were like some chances they may get some attention. We also have integrity check on block header, and this is a very good obstacle in brute force attacks, so we can detect this very early on. And we take the stand to terminate on errors much earlier, which was not the case before. And we also look at the heap changes that they have a small common ground with previous heap management. So beside the variation on dynamic variation and the algorithms and so on, it's also the heap itself, the structure itself changed a lot. So this is a very interesting point for the portability of the exploits, because they need, in order to run on Windows Vista and also run on XP and Windows 2000 and so on, it needs to find that common ground, or it has to kind of handle differently the heap structures and how can it take advantage of that. And the security enhancement are just a journey. So we are going to improve as we find, we learn about new exploits and new methods and so on. And Most important is that application developers need to understand that the mitigations are not a substitute to the real fix. This is just, like some barrier in the, in the way of the exploit, but every single bug, every single security vulnerability needs to be fixed. And in Microsoft, we have this culture, and I hope everywhere in application developers the same thing. So now to show the security enhancement, let's see how we look from the application, from the performance and reliability perspective. And here we can see that we improved a lot of scenarios for multiprocessing and multi-core processing and multiprocessor scenarios. We addressed a lot of critical external fragmentation scenarios, and also we have a better scalability with large heaps. We improved the reference locality on 64-bit platform by default. It used to be this mostly on only on low fragmentation heaps, starting with Windows 2003 Service Pack 1. And we resolved problems that were exhausting the virtual address space. And also we increased resilience with some mixture of long-term allocation with short-term allocations that may cause severe fragmentations. I'm going to show some graphics and some numbers on top on that. So the key enhancements were with the automatic tuning. We have a very low granularity and tuning the heap algorithms and tuning the policies. And we have extensive use of lazy initializations to reduce the heap creation cost, which used to be a problem for low fragmentation heap in the earlier versions. And the most significantly was actually the entire segment management redesign. Currently, there is this exponential growth that, as mentioned before, is handled differently. There is an unlimited number of segments, which allows us to have a very good performance on 64-bit platform or 64-bit platform from now on, and how the application increase is going to be very, very well affected. And we have improved also internal lookups algorithms. Most of them are constant time algorithms when it used to be sometimes linear algorithms and so on. And you can see some numbers later how we address those numbers. So here is a benchmark, which is multi-threaded applications, which allocates concurrently for multiple threads, like random blocks in the range of 0 to 1K, and the second graph is from 4 to 8K. And you can see the blue line. I'm not sure you can read the letters here, the text there. The blue line is for the Windows Server 2003. And this is, and the red thing is Windows Vista. This was running on an 8-processor machine, 64-bit, 4 real processor dual core. And you can see in this range from 0 to 1K, the leukocytes were used before, and the performance was affected by the processor trashing the cache lane from one to each other. And you can see kind of a steady performance. Even if you have like 8 threads and 8 processor, you don't get too much of the throughput that you could in an ideal scenario. While in Windows Vista, we detect a lot of the contention at runtime, and we scale up very close to the ideal case, where we get a very high performance, such as almost close to 8x when you have running this on 8 processors. And this is not actually even the worst case. The worst case is actually when you don't even have random distribution of the blocks, is when you have one block size allocated from all these threads at the same time, because this actually increases the chances to trash the cache line from multiprocessors. And the graph in the Windows 2003 will be even worse than this. You would see similar performance with low fragmentation heap Windows 2000. However, the application explicitly needs to initialize the low fragmentation heap, and it was a large footprint involved with this to begin with. And if we go to larger blocks where the leukocytes were not used, we see the numbers actually, the improvements are actually even much significant. And this is, the low contention, it's telling its word there. where you have significant, like an order of magnitudes difference in performance in the same scenario. Now, I mentioned there are some patterns with the segment management and the way we manage the blocks that some large applications were seeing. And you can see this is a pattern which exposes long-term allocation of 8 bytes. And you can see that in time, actually, the overall cost in address space was around like 4 or 5 kilobytes for every single 8 bytes usage. And you can see that also commit size is around like 500 bytes for every block, and everything at a very high cost. If you look at the performance, the cost of having those allocations, of having the heap operations was very high when the heap was fragmented. And you can see like how the improvement also went in this area as well. Another way to look at this. This is like a different pattern that exposed fragmentation before. You can see kind of across the, in kind of broader, large pattern usage, you can see like 7,000 times improvement in those scenarios. And obviously, this is not happening in every single application. This is not happening in every single server process. But this may be a part of like a fraction of the overall performance cost that some big applications or server were seeing. Just one more thing on this side that I want to notice. This is, just a test which allocates, 2 gigabytes of memory in different block size. So I would just like you to notice that the reserve size is having a spike from like 2 gig to 4 gig when a new segment was allocated before because of the exponential growth in segment size. And in Vista, we have the segment size, the virtual address tracking very well the commit size. So we are going to come to the end of the talk. So as a summary, the attacks get more sophisticated, but so the heap management. And it's not only for the security perspective, it's not only for the security, it's also for the performance. And we made a big step to lay down the foundation to increase our agility to respond to new exploits and respond to new way of people taking advantage of the heap structures. And also we have a stand to reduce the risk of compatibility in the future. So we expect like many years from now, the compatibility bug is going to be lower and lower. And at the same time, we had significant improvement in multiprocessing, in multi-core multiprocessing, and we handle better large fragmentation scenario, large heaps and fragmentation scenarios. And we are not yet done. So we are looking to innovate even further. So I'm looking for feedback for you guys. And my alias is adrmarine@microsoft.com, or you can send also mail to this alias, heapex@microsoft.com. And you can find the debug tools that I used in the demo at this link and the application verify. I'm not sure you can remember the application verify link, but if you just search for on the download side, you can find this very quickly. So next, we're going to hear from Tony about the life cycle and Internet Explorer 7. And I can take a few questions, right? Okay, so I guess so. Thank you very much.